This is GATE 2014 set 2 electrical question number 11. Assuming an ideal transformer, the Thevenin's equivalent voltage and impedance as seen from terminals X and Y for the circuit in the figure are given by this. Now we are asked to find the Thevenin equivalent voltage and impedance as seen from this side. Now for this NPTEL reference, you can refer to lecture number 54, Thevenin Theorem of the NPTEL course Network Analysis by Professor Taposh Kumar Bhattacharya, Department of Electrical Engineering, IIT Kharagpur. For this, you need to know that Thevenin's theorem helps in reducing a circuit across 2 points across which the load is connected, and helps us in reducing the circuit to an equivalent circuit consisting of a voltage source, which is known as the Thevenin voltage source, in series with the equivalent Thevenin resistance. Now, in order to find this Thevenin resistance and this voltage source, that is equivalent voltage source, you need to follow the steps, that is the Thevenin reduction technique. For example, we have a complex network and across these 2 points we have a load connected. Now first step is to remove this load and then find this open circuit voltage, which is VOC, and this is equal to V Thevenin, so Thevenin voltage, this one. Now once you determine the Thevenin voltage, you find the equivalent Thevenin impedance. So this is impedance, making it generalized. Now to find the Thevenin impedance, what we do, we deactivate the active sources by shorting the voltage sources, that is the ideal voltage sources, to short circuit the ideal voltage sources and open circuit the ideal current sources. Now all the independent active sources are deactivated. Now once we deactivate the independent active sources, all we are left out are with passive components, so then we determine the equivalent impedance as seen from these 2 points, and this will give us the value of the equivalent impedance or the Thevenin impedance. So we have the Thevenin voltage, now the Thevenin impedance, then we can connect the load back across these 2 points. So this is Z Thevenin, this is V Thevenin, this is ZL, which is the load impedance. Now with this information, we need another information, that for the transformer having turns ratio N1 is to N2, if you apply V1 voltage, we will get V2 voltage on this side, and if we have an impedance like this Z1, the transferred impedance Z1 dash can be determined by power balance. Once we do power balance, we see that Z1 dash value is Z1 into N2 by N1 whole square. So N2 is the secondary number of turns, N1 is the primary number of turns. If N2 is more, that is step up transformer, the transferred impedance Z1 dash value on the high voltage side is more. This is always true. So impedance increases on the high voltage side, kindly note that. Now coming back to the solution, the applied voltage is sin omega t. So as seen from this side, voltage will appear across these 2 points. Since no current will flow, the voltage across these 2 points also sin omega t. Now once these 2 points have the voltage sin omega t, these 2 points, that is X and Y, will have the voltage 2 into sin omega t, because this is a step up transformer. So 2 sin omega t is the VTH, that is the Thevenin voltage as seen from this side. Now we already know that if the impedance is 1 ohm on this side, the impedance, transferred impedance, that is, so if this is Z1, then Z1 dash is Z1 into N2 by N1, which is 2 by 1 whole square. So this is 4Z1, which is equal to 4 ohms. So there is 1 dash, which is the value of the Thevenin impedance as seen from the secondary side, that is XY, is 4 ohms. So this is the value of Thevenin impedance, and this is the value of the Thevenin equivalent voltage. So 2 sin omega t and 4 ohms are the answer. 2 sin omega t and 4 ohms. So option A is the correct answer. Thank you.